Welcome to Visual Algebra Lecture 2.3, Dihedral Groups. In the beginning of this course, we saw the symmetry groups of the triangle, square, and hexagon. All of these are special cases of a more general family that we're finally going to give their proper name to and study as a whole. Formally, the dihedral group, Dn, is the group of symmetries of a regular n-gon. It has order 2n. One possible choice of generators is the following. A counterclockwise rotation by 2 pi over n radians, we'll denote by r, and a flip or reflection across a fixed axis of symmetry that we'll denote by f. Usually we'll assume that this is a vertical axis, just for convention. Using these generators, one of many ways to write the elements of Dn is as follows. The rotations are just powers of r, 1, r squared up to r to the n minus 1. And the reflections are powers of r followed by a flip f. Of course, there are other ways. Some books like to write f first and then powers of r. But we'll stick with this convention because I think it works better with Cayley graphs. It is easy to check for any n-gon that Rf equals f R inverse. And remember, we are reading from left to right. So here's an example for this square. Let's start with this square up here. And if we rotate it and then reflect about this vertical axis, we get this configuration. And we rotate it one more time, we get this. And then we look at these two and say, how do these differ? And indeed, these two things differ by a horizontal reflection, f. And it's easy to see how this will work for a pentagon, hexagon, etc. Here are several different standard presentations for Dn using r and f as generators. So we say that r to the n equals 1, f squared equals 1, and then we have to specify what this motif is. And this little motif is really the same in all of these, and it's RFR equals F. That's one way to write it. Or you could say RF equals F R to the n minus 1. Or you could say RF equals F R inverse. Some people say RF squared is the identity. So any of these are fine. In the lecture and presentations, we talked about how this relation actually technically implies this one, which is pretty surprising. But I still like including both of these just to make things easier for the reader. Now here's a warning. Many books denote the symmetries of the n-gon as d2n instead of dn. I really don't like this. And here's why. A strong advantage to our convention is that I can write Cn generated by r, which is the powers of r, as a subgroup of dn. If you use this convention here, and then C6 is not even a subset of D6. C6 naturally is a subgroup of D12. But really, I think the subscript should denote which roots of unity are along the outside. To me, that makes the most sense. And I think having a Cayley graph foundation makes that even stronger. I know Dumbin and Foote uses this. A few other books do. I think it's probably more common to use what we're using Dn instead of D2n, but I should point this out because you'll probably see it. Another canonical way to generate Dn is with two reflections. We saw this in the first lecture for the triangle symmetry group. Now we can't necessarily use any two reflections. For example, if we have a hexagon like this, and we try to use this reflection and this reflection, then we're only going to get 4 symmetries, Klein 4 group. But if we use consecutive reflections, so let's say F and FR, or RF, and I'm going to call one of these S and one of these T, just for convenience. If we compose these in either order, we get a rotation of 2 pi over n radians. And we can see that algebraically, ST is F fr, which is r, because f squared is 1, and ts is frf. We could swap the order of this by changing the exponent to r to the n minus 1, and now we get f squared, so we get r to the n minus 1. So this is a rotation that's counterclockwise and a rotation that is clockwise. A group presentation with these generators is as follows. dn is generated by s and t. Both of these have order 2, so s squared and t squared are 1. And then we say that st, we know is a rotation, to the n is 1, because st is a rotation of 2 pi over n. Using these generators, here's how we can write the words. They're alternating letters in s and t. Notice that they're alternating because anytime we have 2 in a row, that's the identity. And if there's an even number of, or if there's an even length, then those are rotations. And if there's an odd length, those are reflections. So here's an example of here's a Cayley graph of D3. Here's a Cayley with the generators R and F, and here it is with the generators S and T. So in general, the Cayley graph is going to be a 2 n-gon. So for D4, we're going to get an octagon and so forth. There is an infinite dihedral group denoted d infinity. And if you think about the n-gon, it may not be clear as to what an infinite n-gon is, but algebraically, we can get this by removing that relation that r to the n has to be the identity. So d infinity is generated by r and f, subject to f squared being 1 and rfr equaling f. Here is a Cayley graph with this generating set. We've seen this before, remember? This is a Cayley graph of several of our frieze groups. Just to remind you, I think we saw one, I'm not going to write diamonds, I'll just do lines. So this frieze, I think if we do this frieze, and then if we do that one where we have those chiral shapes, all of these, the symmetry groups are the infinite dihedral group. We can also generate d infinity with 2 reflections that I'll denote with s and t as well. So these are f and fr. That's one choice with the previous presentation. And I say reflections, not just because that's the analog of what's happening with dn. We don't have an infinite n-gon, but also in the frieze case, these actually are 2 reflections across consecutive axes. Here is a presentation with these generators. It's generated by s and t, subject to s squared is 1 and t squared is 1. And then there's no other relation. So the elements in this group can be written as alternating words in s and t's, so like s, t, ts, etc., STS, TST, STS, TST, so on. And the ones that have an even length are all rotations. They're orientation preserving. And the ones that have an odd length are reflections. Those are orientation reversing. And in putting those in quotes, because there's not really an infinity gon, but if you go back to the frieze groups and you look at these things, these actually are, at least in some of the settings, rotations and reflections. Now let me clarify that last statement. In those 3 frieze groups that I showed you, one of them consisted only of rotations, one of them consisted only of reflections, and one of them consisted of half rotations and half reflections. If you remember that, it was like the even reflections and the odd rotations, or maybe vice versa. In that setting, these will be rotations and these will be reflections. Let's talk about the cycle graphs of dihedral groups. Remember what an orbit is. An orbit of an element is just the cyclic subgroup it generates, so all powers of it. The maximal orbits of Dn consist of, there's one large orbit of size n consisting of all of the rotations, just powers of r, and then every reflection generates a size 2 orbit containing itself and the identity. So here's what the cycle graphs look like. They have this one large orbit of rotations and these n orbits of reflections. And generally, remember, we only include the maximal orbits. So D6 has an orbit. So the orbit of r squared is 1 r squared and r to the fourth. The orbit of r cubed is 1 r cubed, but we don't draw the edges because they're contained in this larger orbit. Now, I'm coloring these nodes red to note the fact that they are rotations. I've been using red for that generator in the Cayley graph. And then the colors up here, there is a method to them, and we'll see this again. The blue ones, well, this is S, which I've been using for the blue edge. And one of these, I think this one was T. But I want you to notice, at least when n is even, that there's a fundamental difference between these blue generators and these blue reflections and these green reflections. The blue ones, I call them side bisecting reflections because the axes bisect sides. The green ones, I call them corner bisecting reflections because the axes go through two corners. I say they bisect a corner, right? Bisect the angle, but just the side bisecting, corner bisecting is easier to say. And then when n is odd, every axis goes through a corner and a side. So I'm going to color those purple. And as we'll see, there's something fundamentally different about the side bisecting versus the corner bisecting reflections. I'll give you a spoiler. They're in different conjugacy classes. They're not similar in terms of matrices. But when n is odd, all of these things all have the same structure. So these will be a single conjugacy class. If you know what that is, great. I don't expect you to. Otherwise, we get, for n is even, we get two types of reflections that are fundamentally different. And we saw that in frieze groups when we, you guys remember we had a frieze, and we had these diamonds. Pretend these are diamonds. I don't want to draw them. And then there was a difference between an axis like L0 that was through a diamond, and then L1 that was that bisected a diamond. So this is the analog of that for the finite dihedral groups. The separation of dn into rotations and reflections is visible in its Cayley tables if you order the elements in the correct way, or if you group them. So the first four are all rotations and the next four are reflections. If you do that, and you look at this internal table and you squint your eyes, you might see some patterns. Namely, everything in here is a rotation, everything in here is a reflection, and similarly down here. So this is an example of a quotient. We saw these in the lecture on Cayley tables with the quaternion group and with the three light switch group. And it's a way to shrink a group to get a smaller group. And so this, if you squint your eyes, this actually has the structure of the Cayley table of this group of size 2, which is really just C2. So it's saying if you have any rotation applied to a rotation, you get a rotation. If you have a reflection applied to a reflection, you get a rotation, and then a rotation with a reflection is a reflection. We'll see a lot more examples of this going forward. I just like to point them out as they occur. I want to conclude this lecture with a discussion about the representations of dihedral groups by 2x2 matrices. Recall that the Klein 4 group can be represented as follows. This was the identity matrix. This next matrix flips the value of the y coordinate, so that's a vertical reflection. The next one flips the value of the x coordinate, so that's a horizontal reflection. And the last one is a 180 rotation. Moreover, a rotation by 2 pi over n radians can be represented with a real rotation matrix that we've seen in the previous lecture, or a complex rotation matrix that we've also seen. Can you think about how to get a representation of dn with these matrices? Here are two ways. First, we can do the canonical real representation of dn with 2x2 matrices by taking the real rotation matrix. I'm going to call this one A. And then we take either of these reflection matrices. I like to use this one because it's a reflection about the y-axis. So it's like complex conjugation. And let me call this one, so that was V for vertical reflection. Let me call this V. And now how would you check that this is actually the group Dn and not some other group? Well, it's not too hard to show that, I mean, it may be a little tedious, that there's exactly two n matrices generated by these two things. You can write them out. You can use, I think there's a nice online matrix calc. If you Google that, that allows you to quickly compute matrices and powers of matrices, and it handles complex numbers, so it's very convenient because doing it by hand, you'll make mistakes. But what you can do is you can check that these two matrices, A and V, satisfy A to the n is the identity, satisfy V squared is the identity, and then what else is there? So remember that relation in the Cayley graph, this little motif that persists. So if you start anywhere, then you can check that, red, blue, red equals blue. So you can just check by hand that A, V, A equals V. And once you have a group of size 2n with these relations, you know that it has to be Dn. And if you're not sure why, or maybe that seems like a little hand wavy, this can be formalized and proved rigorously, and that's done in chapter 7 on universal construction. So if you want the formal proof of this, wait until then. Next, the complex representations of Dn with 2 by 2 matrices is similar. We just use this complex matrix, Rn, and the complex reflection matrix. So let me call this one R. Instead of Rn, I'll just use R, and then let me call this one F. And remember what F is F is, let's see, where do I want to write it? F up here is a map from C2 to C2, and what it does is it sends Z1, Z2, just swaps its coordinates to Z2, Z1. So it really is like the reflection that swaps the first two coordinates of C2. And you may remember earlier in the last lecture that I said this is a nice rotation matrix, and I said, well, there's others. You know, you could put a positive sign here. It still is going to have order n. You could put a negative sign in front, or you could mix and match those things, positive sign, negative sign. And so why this one? Well, if you put a negative sign in front, it might not work if n is odd, I think. But the reason why this is the rotation matrix, the standard complex rotation matrix, and not like this is positive, is because these two matrices generate Dn. I think we can all agree that this is a canonical reflection matrix for this reason up here. And this is the matrix with R that satisfies the relation R, F, R equals F. And if you change these signs here, it's not going to work. You're going to get some other group. So, and of course, you have the relation that R, the n is the identity, and F squared is the identity. So this is one more reason why I like to call this group Dn and not D2n, because n is all over the fingerprints of this group. Like calling this thing D2n and having these roots of unity for where you're off by a factor of 2, and the fact that you could just take a rotation matrix and Cn and add a reflection matrix to get Dn, I think that's much more natural than have to worry about going from Cn to D2n. Okay, so that's the end of the section on dihedral groups. What we'll do next is talk about abelian groups. Every cyclic group is abelian. Dihedral groups are not, unless n is small enough. I didn't say it, but you can define the dihedral group D2 and D1. You can't say it's the symmetries of a 2-gon or a 1-gon. I mean, I guess you can sort of say that the 2-gon might look like an eye like this. But if you just take the same presentations for all Dn and you just let n equal 2 and n equal 1, then you actually get legitimate dihedral groups for n equals 1 and n equals 2. And at least for n equals 2, you can check this. You get the Klein 4 group, which really is the symmetry group of one of these little eye-shaped things. One of these eye-shaped things that will have these different axes of reflection. And so it does make sense to say that the group D2 is V4, and then D1 is just, it's a group of order 2, because it has order 2n, and there's only one of order 2, that's C2. Okay, I think I'm going to leave it there. See you next time with abelian groups.